it's live. Everybody else is going to be hearing it on YouTube. But I'm glad Camtasia's working. That's sweet. Okay. So let me just do my own little deal on power factor, and to do so, I'm going to bring up a document that I actually prepared, for a professional engineering client not too long ago. I will not share the proprietary information because I have an NDA with these guys, but this, just to let you know, this stuff is for real. So there's a company called Power CEO, and they make a power factor corrector somewhere in this manual. So this is a manual for a Fluke 4041. I'm just going to do a quick search for power factor in the manual. Okay, so the first thing to know about it, it's going to be somewhere between 0 and 1, and it's a well-known. There's no real other documentation on there, but it is a well-known electrical power metric. I'm going to show you a little statement of work that I put together for them here. So what they wanted to do is actually measure kVA, which is the long side of the power triangle, somewhere down in here. Let me see if I can find it. Yeah, so power factor, kVA, and kVAR, and all three are related. And let me just show you how they are related. So I put together a final report. And the best way to do this, I think, is visually. So again, I gave a little report on this 5-step power factor corrector. And I did it with several different power factor correcting devices that they have. So there it is, kVAR, kilowatt hours, both measured and reported. So all of this is very well known. I'm not going to cover it. It's NRGY 101 stuff. Okay, so here are the three things. Prepare an engineering report for true power, which we call P, reactive power, Q, and apparent power, S. And if we go and draw those on a triangle, I'll do my best to just draw that. There's one leg of the triangle. Here's another leg, and then here's a third leg. Down here is P. So I can make that a little bit larger. There's P. Go back to my other document. Apparent power is Q. This Q is up here. Then reactive power is over here. Oops. So the third leg of the triangle is reactive power, and we call that S. Okay, and so we know from the Pythagorean theorem that Q squared, and I'm just going to use the arrows here, so Q squared equals P squared plus S squared. Drag that out so you can see it, maybe. Hold on. Software isn't quite as slick as, oh, there we go. Okay, so Q squared equals P squared plus S squared. And I can get down into a definition of those three. And online, if you want to take a look and dig into this a little bit more, Falstad.com circuit, LRC, that just stands for inductor, resistor, capacitor. So you've already taken NRGY, or sorry, ETEC 106, so you know what those are. The inductor is typically a coily looking unit. The capacitor is these two straight bars, and the resistor is this sort of Charlie Brown looking thing. And any LCR circuit, as it's called, is going to have some combination thereof. A power factor corrector, sometimes it's easier if I can see myself. I'm not sure why I'm not really able to see myself that well. Hang on. Oh, I guess I'm that tiny little thing down there. It's just somehow easy to talk if I can see myself. Anyway, what a power factor corrector is trying to do is just make the entire circuit appear to be a resistive element. So what that looks like on this triangle is nothing along this this Q line, and sometimes this is also Q is sort of equal to volts times amps, whereas power is just equal to I squared R. And you're like, okay, so how can these be different? Well, how can volts and amps be different than I squared R? Well, in an LCR circuit, like we're seeing here, you can have current sort of sloshing back and forth in this inductor and this capacitor kind of forever. You can think of it like a bathtub where it's just sort of sloshing back and forth and never really dying out. And so what can happen in a power circuit is that that amperage can sort of leak back through the mirror or through the meter back out to the grid, and you've sort of already paid for it, but you're not actually getting the benefit of it, and it tends to screw up the grid. So what we're trying to do is take this line in a power factor corrector and actually bring it down here. So this line, let me see if I can recolor that thing. Well, this line that I'm sort of scribbling on right here, or that I'm sort of redrawing, this is a preferable power factor down here, whereas something that's up top, this is a high power factor. So big triangle, big power factor, small triangle, low power factor. If you're down here, near the bottom, let me just see if I can copy this again. Got the line thing turned on. There we go, copy, paste that. This is, and I'll just write it as PF now. PF equals 0, and if you had something, and this is almost never going to happen, but if you had something that was more or less vertical, I think I can draw it vertically. If you had something up here on this triangle, copy, paste, this would be a power factor equal to 1. It would just mean that all of your electricity was just sort of flowing through the circuit in an inductor or a capacitor, never really getting used. Okay, so that's a little bit of the theory on it. You might also go back out and look at these phasor diagrams. They're showing, again, this is sort of, what the real power, and this is that, well, imaginary power or non-resistive power. There are a lot of different calculations for it. I'm not going to dig too deeply into that. It's kind of a technical engineering document. But you can see that there are multiple ways to configure LRC circuits that will affect exactly how the power factor or the kV and the kVAR look to a meter. Okay, and I've drawn a mechanical analogy here showing that, again, a bathtub or a tube, you could have a system that's sort of rocking up and down. So this is just a 4-bar linkage here. This is a mechanical analogy. Each one of these little pins is like a resistor that keeps the thing in place. The tighter the pins, the less sloshy it is. And the water itself, as you know, just like in a capacitor, would sort of never leave these vessels. And the inductor just sort of allows that water to slosh back and forth. So that's the mechanical analogy of an LRC circuit. Okay, here's another mechanical analogy of an LRC circuit where the goal of this whole exercise is to actually plow the earth, right? So you're trying to take the plow and disrupt the soil. What you don't really want to have happen, but which is going to happen anyway, is the farmer on the back is sort of going to be bouncing to and fro. He's sort of like the mass, which is M, bouncing back and forth, a lot like those electrons through a motor circuit. Likewise, the capacitor sort of is like a spring, so the guy just is sort of bouncing back and forth on this rope. Over here, so the farmer represents the apparent power. He represents Q on that triangle. The horse, on the other hand, represents the reactive power, or S. So any vertical motion on the horses, and again, this is not something you want. I mean, so you use leather straps so that the horses don't suffer a large vertical load. So that's really what's going on here. Now, in terms of calculating it, we can see that if we know, as with any triangle, if you know 3 of the 6 variables, you can calculate the other ones. So if there's an angle here, let's see if I can take this guy, copy, paste. Oh, now it wants to stretch. Okay, fine. If this angle in here is phi, I was right, it's phi. I don't think I know how to do I don't know how to do a symbol font in there. So if that's phi, we know we can get the other variables. So we know that well, what's the best way to do this? Give me one quick second and go back to check another document I have here. There's always sort of a simplest way, and I don't want to make it more complex than it is. I've got one more little PowerPoint for you here. I'll be sure to share this. There's a um, cosine variable. Give me one quick sec. I'll be right back with you. Okay, so guys, I just had a little nomenclature snafu, and you'll notice by looking at the board, I had just transposed S and Q. So S is apparent power, and I'll just write that out. Apparent power. There we go. Make that a little bigger. And Q is reactive power. Make that big enough to see. 48. There we go. Okay. So Q's over here. Reactive power. S is always the greatest. And so what we're trying to do is get S more or less to equal P. So again, P is power, it's true power. The power factor, I was making it too difficult a second ago, I apologize. So the power factor is just the cosine of this angle. So as I said, when the apparent power S sort of comes down and sort of turns from a triangle into a line, your power factor goes to 0. Gosh, I'm not thinking straight today. Power factor goes to 1. Just had Monday and Tuesday messed up. Now I got my power factors backwards. Okay, in this case, this line, and that's why I was questioning myself earlier, this line would never actually be that tall. It would more or less be, it would shrink to a point. So you wouldn't have any resistance at all. So here your power factor is equal to 1 if the apparent power equals the true power, and there essentially is no inductive load or capacitive load. Again, the power factor is just simply equal to the cosine of phi, which is this angle. And again, this angle only becomes non-zero when you have either an inductive load or a capacitive load. Whenever you have an inductor or a capacitor in your system, and we'll just review that one more time. So only LRC circuits with inductors and capacitors are going to have a non-zero power factor. If, however, you can balance an inductive load with a capacitor, then you can bring that power factor closer to unity, closer to 1. And I can show you a little bit too how there is some design work and some engineering work. You can actually overcorrect. Right, so this is the lagging power factor where the phase lags. This is the leading power factor where, well, it leads. So this would be an overcorrection or too much capacitance. Okay, so there is the story sort of physically and mathematically on power factor. So I'm just going to throw it back to Joe for a second. Any questions on that, Joe? Is that clear enough? I had apparent power and reactive power backwards there for a second, but what you see on the screen now is correct, except for the fact that it's P is I squared times R. We don't need that up there. Okay. So sometimes this is called, I'm just going to write it like this, sometimes called kVA. And the K just means that you're measuring it in kilovolt amps. And this is sometimes measured or expressed in kVAR, and the R just stands for reactive. Okay, so and sometimes and so you can see that the power company could charge you for kVAR, it could charge you for kVA, it could charge you for power factor, but at the end of the day, it's just charging you for the same thing. It's just charging you for having an uncorrected inductive load on your system that's sending electricity back that it wasn't expecting to see. And sometimes it's called dirty power. And what it can also do, it can start to mess with the phase of the system. And that might be even more important to the power company. We talked a little bit before, if the demand goes up or down, if the all of a sudden you got a big demand, the phase, the actual 60 hertz phase will respond accordingly. If you then have a lull, the phase will also respond. So these guys at the power stations are always monitoring, oh, what's the overall phase going to be doing out on the line? And you might say, well, shoot, is it the same everywhere? Well, yeah, the grid, the electricity is basically traveling at the speed of light. A light wave can travel around the Earth, what is it, like 6 times in a second? So electricity bouncing back and forth across the U.S. only takes a sixth of a second to get there. So you can imagine that the whole grid that's oscillating at 60 hertz or 60 times per second, the grid speed, the speed at which the grid is oscillating 60 hertz is actually on the same order as the speed of light. So you actually are maintaining a fairly consistent phase throughout the whole U.S. grid, and that's really what this thing is all about, is making sure that the grid stays in phase. It's sort of the mixed blessing of AC power. All right, I think I'm about 30 minutes, 22. I'm going to take a break on that. And then, and really from here, once you sort of understand the math and the physics behind it, it just becomes a financial issue. And we spent week 2 talking about finances. So there are some subtleties, but it's basically just looking at how much reactive power you might have had over a given amount of period of time, and then the utility has a certain charge for that. So once you've understand the physics and can measure what these kVA and kVARs are, and in fact you can, let me just show you some of that briefly. I can show you some of the data that came out of this meter. I'm just going to show you one very simple thing that came out of the meter with a power factor corrector on. You can see that before the power factor came on, my power factor was down around 0.96. Once I flicked it on, it improved closer to 1. And my phase, which was relatively out of phase at 14 degrees, came much closer to 0. Well, it got down to 6. These are the fundamental harmonics involved. Every single wave, a 60 hertz, every single 60 hertz wave. This is basically your 60 hertz right here. This is your 120, your 180, 240, etc. There are all these different harmonics sitting out there. This is DC that have different strengths that comprise the overall waveform, which can be quite complex. The voltage is never a perfect sine wave. It's always looking a little bit a little bit funky depending on what's coming in. So I hope that's clearer. It's not easy. It's a little bit complicated, but that's what motivates the necessity for charging for power factor. So I hope that helps. Sorry to have confused you up front. I think I've got apparent power, reactive power, and let me just clear this or complete this by saying this is true power down here. And this is the legacy of Edison and Tesla. Well, I'm going to take a quick break. I will be back. My throat's already getting sore as I've been sick for the last week, but bear with me. Joe will be right back, and everybody else, I'll be back in the room momentarily. All right, I'll take a quick pause.